This video is all about titrations. This is the virtual lab software that came with your book. This is the titration part. In this burette, we have NaOH. In this beaker, we have a weak acid. Also in the beaker, we have a pH probe. This pH probe is going to measure the pH in the beaker as we add the NaOH to it. This is the kind of thing you're going to be doing in your lab. You're going to be putting NaOH here in this burette and acid down here, and you're slowly going to add the contents of the burette to the beaker. So let's do this. There it is. We can let it add kind of quickly at first. And you'll see that we have the pH beginning to be measured here. Now at first, and you can do this when you do your own lab too, you can add it pretty quickly at first because you'll notice the pH does not change very much at first. One way to do this in your laboratory is to add it very quickly during one version of the titration. Then when you see where the change happens, you can stop it and go slower through that area the next time. Now, keep your eye on this pH here. It's still very slow, very slowly changing, not really changing very much at all. And then, boom! Look how quickly it's changing through this area right here. And the color changed. And then it evens off again. This is always the shape of a titration curve. Doesn't change very much, doesn't change very much. All of a sudden it changes, and then it levels off again. Now this area of the curve right here is called the buffer region, because in here the contents of the beaker really is acting like a buffer. We've got some of the acid and we've got some of the salt of the acid. That's why the pH isn't changing very much. But then here the pH changes very rapidly because we've reached what's called the end point of the reaction. The amount of acid and the amount of base are equal right in the middle of this quick up and down. And then up here, this is going to even off again because there isn't going to be any acid left in the beaker, just some base. When we think about doing math for a titration, this is really stoichiometry. At first, you've got some acid in the beaker, and you're adding very slowly some base, some OH minus. So the very first thing you're going to do is a stoichiometry step. HA plus OH minus gets you to water plus A minus. So you have some moles of HA in your beaker that stays constant, some moles of OH minus that changes as you keep adding it. None of this, none of that. Well, this we don't care about. And none of that at first. Then you're going to do stoichiometry. Before the end point, the OH minus is going to be your limiting reagent. So you're going to end up with 0 of this, some other number of moles of this, and some number of moles of this, just like in those buffer problems we've been doing. Then course, don't get confused because I wrote moles here again, but that moles isn't the same as this moles. It's this minus this. That's what this part is. And this is going to be the same as this. But now we've got HA still in equilibrium with H plus A minus. And whatever number is here is what's going to go there. Whatever number's there is going to go there. I have none of this. I do the whole usual icebox, and I find the pH. That works totally well until you get to the end point. At the end point, when I say HA plus OH minus goes to H2O plus A minus, this number and this number of moles are going to be the same. I have none of this and none of this after the reaction is done. I have only A minus in the beaker, which means when I write the icebox, I can't write HA in equilibrium with H plus A minus. I don't have that in the beaker anymore. There is no HA. So then I have to write, at the end point I have to write A minus plus H2O is in equilibrium with HA plus OH minus. And instead of using Ka, I use Kb, the Kb of A minus, which remember you find by saying Kw over Ka. And then I find the OH minus concentration, the pOH, and then from there I get the pH. That's at the end point. You'll notice, unless I'm talking about strong acid and strong base, the pH at the end point is not 0. In this scenario, the pH at the end point is going to be basic, because all I have left in the beaker is a weak base. The other important place to notice in a titration is something called the half equivalence point. The half equivalence point is exactly what it says. It's halfway to the end point, or to the equivalence point. It's the point where, when I'm doing the stoich step, I have HA plus OH minus goes to water and A minus. It's the point where whatever moles this is, this OH minus is half of that moles. So that when I do my whole IE thing, this is 0, this minus this is half of what it originally was, and this is also half, because this is equal to that. At that point, when I do my icebox, when I do HA is in equilibrium with H plus A minus, and I do my whole icebox, I'm going to end up with Ka equals X times half of moles that I originally started of HA minus X over that half moles plus X. If I'm neglecting X, these guys are canceling, which means pH is negative log of X, but X equals Ka. So at the half equivalence point, the negative log of the H plus concentration is equal to the negative log of the Ka of the acid. pH equals the pKa at the half equivalence point. Which means, if you have an unknown acid, if you don't know what acid you're titrating, if you know the pH at the half equivalence point, you can find the pKa. From there you can find the Ka, and there you would know what acid you were doing. So this is a very, very important place, the half equivalence point. Now, the other thing I want to talk about is this color change. The reason the color changes is because we've added an indicator. The lab that you are going to do, the indicator is phenolphthalein. What an indicator does is it reacts with the base, or whatever it is that's here in your burette. That's why when you're doing the lab, you'll notice it turns pink, and then you swirl and it goes away. The indicator is chosen specifically to change color near the endpoint of the reaction. And if you look in your book, there's a whole table of indicators and where they change color. What happens is the phenolphthalein, for example, is a certain color. It's in fact colorless in acid. But when it reacts with base, the structure of the molecule changes in such a way that the molecule is pink. But the base would rather react with the acid than with the phenolphthalein. It's only when there's no more acid in the beaker that the base will react permanently with the phenolphthalein. That's why you want the palest permanent pink you can get when you titrate. Because really, the base that's turning the phenolphthalein pink is extra. You don't really want to count it. So you want the palest pink you can get so that you know you have added just the right amount of base that totally reacts with the acid. Now as for the shape of this curve will always look like this, where I'm adding a base to an acid. If I was adding an acid to a base, it would actually start out up here and come down. If this were a strong acid and a strong base, it's actually a little sharper. The transition happens a little quicker. But for the most part, the shape is always the same. Half equivalence point is somewhere around here. Equivalence point is somewhere right there in the middle.